Alright, number 5 says, use the figure on the right to answer the following. Determine what the derivative is at 1, 2, 4, and 7. So if I'm looking at 1, 2, 4, and 7, I'm looking for what is the slope at those points. So let's go ahead and look at the graph, and we're going to draw small little tangents next to those points. So you can see at 1 there is a horizontal tangent. You can see at 2 you also have a horizontal tangent. At 4, basically these are easy to see because they're just linear graphs. But at 7 it's a little bit different because you have something that looks like this is the tangent. So the first 3 were easy to see because they were all on a line. The other one is on an actual graph that is variegating, basically changing throughout. That's that quadratic piece there. So if I wanted to determine for this at x is equal to 1, it's just a horizontal line. We're going to say f prime, I'll write it up here, f prime at 1 is equal to 0. F prime, or the derivative at 2, is also equal to 0. F prime at 4 is just what is the slope of this line right here. Well, from a corner to a corner I have up 1 over 2. So it's a positive 1/2. And then finally f prime at 7, it looks like it's going to be a horizontal tangent. It's going to also be 0. Alright, so now let's go ahead and go to B. It says, for which values of x is the derivative less than 0? Now we've talked about this many times in class. The derivative being less than 0 shows that your original function, your position function, is going to be decreasing. Because the derivative was negative, the original function f of x is going to be decreasing on that interval. So looking at this, we're going to see when it's basically decreasing. So let me go ahead and come over here, and I'm going to look at when is the function decreasing. Okay, so just a reminder, this is our f of x, and we're just wanting to see when it is decreasing, and it's decreasing right here. That's where the derivative will be negative or less than 0. All these the slopes of all these tangents are in fact going to be negative. Alright, so for which values of x, we're just going to say x is from 7 to 9, and it's an interval notation is what it's going to be. So between 7 and 9, non-inclusive, that's whenever this slope is going to be negative, because that's when the original function is decreasing. That's part B. If we look at C, which is larger, the derivative at 5.5 or the derivative at 6.5? Let's go to 5.5, which is here. We can say that's a good approximation as far as the tangent. At 6.5, it's a bit less steep. So which is larger? Obviously, the larger one is at f prime of 5.5. And then part D. Do you think that the derivative at 3, so the derivative at 3, exists? Explain why or why not. So the derivative at 3, knowing from what we have learned as far as functions go, when it's differentiable, we know 3 different times when it's not differentiable. At a cusp, at a vertical tangent, and at a discontinuity of some kind. That's when it's not differentiable. So if I have like an absolute value, I cannot tell what the slope is here. If it was given to me piecewise function, I could define it as either being a -1 or a +1. But this is just saying in general. So we can't use it as a piecewise function if it doesn't give you the piecewise function. Vertical tangents look something like the following. You can have something that's like this, to where at this specific x value there is a a vertical tangent. That is also not going to be differentiable at that x value. And then obviously the discontinuity. If I have something that is discontinuous by either jump, point, or removable point, a jump or an infinite, they will not be differentiable. So because this one is a cusp, we have this extreme change from a slope of 0 to a slope of 1/2. It's not gradual, it's not a smooth curve because it is a cusp. That's the explanation of why f prime of 3 does not exist. And that's it.